Hi, I'm Jack, the product manager for CARA VR, a suite of plugins for Nuke for dealing with 360 video VR material, covering everything from stitching through standard comp workflows to headset review. This is the second of two videos related to stitching this shot and part of a longer series covering the full post-process for this particular material. In the first stitching video, we went through the basics of pulling a template for this rig with C Camera Solver, colour matching the various cameras with C Colour Matcher, and deghosting with C Stitcher. In this video, we're going to look at further refining our rig template, the use of user matches, as well as tuning the result with a variety of techniques including manual patch-ups. We're going to be using this shot from the mission, courtesy of New Deal Studios. Now that we can see the result of our template post-stitcher, it's a good time to get in and do some final refinement. The techniques we're going to apply could equally have been used before, but previously with this particular shot it wasn't obvious they were required. Now panning around inside this shot, we can see that in certain overlapping regions the alignment isn't 100% perfect. It's looking pretty good, but let's see if we can do a little bit better. As we mentioned in the last video, it's possible that some of these misalignments are down to the fact there's a huge depth range within this particular shot and that fixing them would require splitting out into different depth layers. But I suspect that's probably not the case here because certain overlapping regions show a bit of ghosting whilst others at a similar depth range don't. Let's kick off though by tuning the convergence a bit. So we did this before on Camera Solver, but now that we can see the actual final quality stitch, we should probably have another look at it. Now obviously this takes a little bit of time to render here because it's going to need to regenerate vectors for these different convergence depths. So let's see if this makes any difference. So we can bounce before and after our adjustment. So not a huge amount here. How about in the nearby objects? A little bit in the hair, which makes me think that that convergence depth is too close. So this is quite an unusual piece of material because it's shot with quite a large size of rig. Normally with a lot of the smaller size rigs that you see, generally like 10 meters convergence may be the max that you'll really see differences, but here because we've started with a 30 centimeter baseline in the actual rig, maybe we should try going further out. So let's, again, before and after. Yeah, okay. Trees are starting to be a little bit more concise with the longer convergence. Let's try pushing it even further. So it's stopped making such a huge difference at this point, but there's still a little improvement. So let's push this out to 80 and I reckon we'll be done there. Yeah, okay, let's go with that. If we wanted, we could also adjust our filtering. As usual, this is a bit of a trade-off between compute time, sharpness and ringing, so let's stick on cubic for now. Let's pop back to our camera solver. This also has the convergence control, in this case for the preview stitch output, as does the colour matcher in fact. So you might as well look at dialing this in, and if you're going to spend a lot of time tweaking them and still bouncing between the different views, you may even want to expression link them together. This can really help when there's a moving camera rig, as it means that when there's no features in an overlapping region on one keyframe, there might well be in another. Generally you don't need massively frequent keyframes, which is why the default's at 500 frames. We've only got a few hundred frames worth of footage here, so let's do something like, oh yeah, something like that should do the job. As an aside, there's one somewhat hacky but potentially useful option, which is this solve for animated camera setting here in the settings tab. With this off, which is the default, and what we're actually going to do in this case, the solve uses all the various keyframes for a single template. With this off, which is the default and what we're going to do for this particular case, the solve uses all the various keyframes for a single template. With it on, the template itself is actually animated between the various frames you set as keyframes. I say it's hacky because you shouldn't need to do this. The rig shouldn't be changing. It can, however, be useful if you're using the lens distortion per camera, potentially with the nodal option mentioned in the first video, because initially you're technically cheating the rig template to take into account the scene depths and disparity. By allowing that to animate over time, you're able to take into account changing scene depths if, say, the camera's moving. I definitely wouldn't recommend this for stereo work, however, as for stereo stitches we need the template to be as geometrically correct as possible. Now, by matching again, I'm going to lose all the work I put into refining from the first video, since it's going to be a whole new set of feature matches we'll be working with. And this is why when I hit this button, it's actually going to warn me. Since we're going to lose the solve anyway, let me hit reset to demonstrate something else whilst we're here. With certain solves, not this one, you can fail to get any kind of feature matches in certain views. As we saw in the first video, depending on the configuration of this parameter here, we can force the solver to search only in overlapping regions, which is what the default's set to. And the reason this works with the none preset case, i.e. this case here, is that all the cameras in my rig are overlaid on top of each other. So every single camera is on top of another, so the entire camera views will be searched. If I'm not getting feature matches in certain overlaps, I can try pre-positioning the cameras into roughly the right places. So for example, let's turn on my overlays. You can see how we've got some rough feature matches here. Let's go back to cameras. And now I could say go in here, select camera 14, and if I know that to be somewhere around the top, I can pull this camera up into that region. And of course, because of the initial alignment, I'll probably want to first of all select all of my cameras up to my top facing ones and rotate them in Z. And this should allow me to position my sky cameras. So by doing this, I can pre-position cameras to give the solver a better chance of finding matches when it goes through the match process. In this case, I don't actually need to bother, so let's reset everything. So now we'll match again. Rather than running this feature match on a single frame, this will now jump through the keyframes that I've specified on the timeline and do the feature matching on every one. We can see how this drops us back off on the frame we started from, which was 5808, which now isn't an analysis keyframe, which means we don't see any matching keyframe data here. So we'll use the utility buttons to hop back to the previous keyframe, and we can see we get those feature matches shown in the overlay again. And now, just like the first time round, we're going to go for a first solve, which is a single focal length with no lens distortion. And then we will get it to optimize for a single lens distortion. So this will tweak the initial layout we got in the first solve to include lens distortion estimation. And I could run that a couple of times. So let's match. So we got our matches. And now, just like before, I'm going to start off by solving with no lens distortion. It's looking good. Let's flip on our optimize single, then we'll refine. Flipping to camera view, we can see that there's some weaker links between cameras in here. Sometimes you even get a case where there's no links for a particular overlapping region. In this specific case, we don't need to modify or add matches, but I want to show you how to handle that kind of thing, so if it crops up in your cases, you can deal with it. If it does happen, you need to either, first of all, try the pre-solve positioning trick I mentioned a minute ago, or post-solve, drag a specific camera into place. So with the default tool, what you get is the ability to both drag multi-select feature points, or if you do a single click select, what you'll get are these sniper preview windows up here. And these show your feature match back against the original source views on which they were found in the orientation of that source view. Just like with tracker sniper views, you can pop in here and you can start correcting these. The Features tool allows you to do the same. It also allows you to add feature matches of your own. Like the other tools on the toolbar, The main action is available on Control or Command Alt click. So I'm going to drop one on the end here. That adds a feature match with matches on every single one of the overlapping cameras. So here you can see I clicked on a region where there are in fact 4 cameras overlapping. And the reason you need to pre-position your cameras to make sure they're overlapping correctly is so that the right ones get populated in here. Now that I've done that, I can pop in and make sure that this feature, whilst its initial alignment is done based on the overlap, make sure that this feature matches correctly across all the views. And you can see how that user match feature there is drawn in a different way, so you can actually identify it from a distance. These user matches also have a higher weighting when you solve or when you refine than the auto matches, which means that if you do add them, you need to make sure they're bang on. But it does mean you can add just a few and it'll sway the solve more than an equivalent auto match would. So now if I wanted to take that into account, I could just pop back in here and do a further refine. Okay, well, I'm feeling pretty happy with our template. So let's go and check out our stitch result. And yeah, I'm also feeling pretty happy with that. Final tweaks you might want to make here. Well, in the first video we traded off having to calculate vectors every frame for having them every 30 frames. So that the overall time to generate 30 frames was lower, but for any single frame within that group it might take longer. The other trade-off was lowering the risk of temporal inconsistency at the expense of potentially less correct results. That worked for our early stitches, but for stereo you're often in the case where geometric correctness rules above all else. So let's dial down the step to 1 and set keyframes for every single frame. Speaking of stereo, how's that looking? It's looking pretty nice. Now we spent a lot of effort working on getting the most true-to-life sense of depth when you've normalised your scene to real-world depths using the rig size parameter we saw before. You may find, however, that you want to exaggerate it a bit, and certainly looking at a lot of the popular 360 stereo experiences at the minute, that seems to be the case. To do that, we can actually expand the IPD between the views rendered, so maybe even up to as high as 0.1. So it's not going to be too noticeable if we bounce between left and right in the viewer, but if you're wearing a headset, you notice a difference between those two. Let's pop this back. Before we move on, I want to quickly touch on one final option in Stitcher. This was introduced in 1.0 v2, so you'll need at least that version, and it's this blend option on the front panel here. By default, it's just doing a straight up alpha blend between the different images. We can instead set it to multiband. This will endeavour to improve the stitch by handling different colour frequency ranges differently, and is particularly noticeable with low frequency colour shifts between the different source views. As you can see here, it's actually helping out in the edge regions, making the remaining localised differences, which C-Colour Match's global approach can't handle, look pretty good. It also has the added bonus of interpolating across unfilled regions by looking specifically at the low frequency colour changes. On the flip side, if you have fast changing colour, this could introduce beating or other such temporal artifacts, so be aware when you employ this. Well, so far we've covered a range of approaches for fixing and tuning stitches. What if none of these work, or you're finding out that when you correct one area, it makes another worse? Well, this is where the manual patch-ups and fixes come in. For the remainder of this video, we'll cover the intended manual patch-up workflow. The idea is that if you work in this manner, you should find handing off scripts or picking up other people's stitches easy. Now, of course, you could do patchwork on the final stitched image, ignoring all the source image streams. This is covered in more detail in the comp workflows videos, but given you've got access to the individual source view layers that make up your stitch, you might as well try and make use of that extra data. What we'll cover now is tools and techniques to adjust the images during the stitch process. Right, well, earlier on we saw that the output of the camera solver, or the colour matcher, in the main view is your preview stitch. Then, in the various cam views, you're looking at the original source camera views in source space with alpha channels added. The areas inside this alpha mask are the ones that the downstream stitcher here will endeavour to use as part of the stitch. For all coincident pixels, it'll normalise the incoming region's alpha channels and then blend based on that. And this means that we can define which regions are solidly one input versus solidly another input versus an overlap between the two. Now, for very coarse level adjustments, I can pop in here and I can actually set my alpha channels by picking one or all of the cameras in here and then dialing in my mask shape and size in here. Now, by default, for full frame fisheyes like this or rectilinear, you'll want to use rectangular, and for something like a circular fisheye or partial frame fisheye, you'll want to use elliptical. And obviously decrease it to match the central circle. We'll stick with rectangular, and in fact the default size and feather are fine. By comparison, the output of the stitcher is your final quality stitch in your main view, plus individual camera views warped into Lat Long Space, again with that alpha mask preserved. This means that we can apply downstream of C Stitcher a C blender. C Blender essentially takes the warped camera views coming into it and normalize blends them to recreate your final stitch from those individual layers. This means we have two places in the script where you can manually operate on these individual camera layers, either in source space between the solver and the stitcher, or in final lat long space between the stitcher and the blender. And what's quite enlightening about the mask overlay when you look at it on the output blender is you can see the regions where there's some normalized blend happening versus the regions where it's a solid input on one particular view versus regions where there's nothing. To then work on the individual views, you'll generally want to split them out using Nuke's split and join functionality. So pop in here, make a bit of space, and go views, split and join. And what this does is it creates a one view for every single view in the script and then joins them all together. This means you can work on just camera view 8 here or just camera view 9 here. In this case, between solver and stitcher, so in source space. I can then similarly do the same thing post stitcher but before blender, and now I can work here in Lat Long Space as well. And the important thing here is that it's maintaining the existing view naming convention. All the CARA VR stitching nodes expect these views to be called Cam1, Cam2 through to Cam-X, Cam whatever. If you change them, reorder them, stick them in a script where you've called them something else, then you're going to be in a world of pain. Now obviously by adding these, Nuke needs to split out these separate views and process them separately. So you are introducing overhead into the script. We'll come back and look at this a bit more in a second. Whilst you're working in this section, you only need to hook up to the downstream stitcher so that it can calculate the main view for you. You could even temporarily drop in another color matcher before stitcher without any analysis switched on, just to act as a preview stitcher, so you can see any changes you can make to these cam views. So what sort of work would you do in the top section versus the bottom section? Well, up here you'll be working on material in source space, so in the original camera view projection. So the sort of thing you'd want to work on here is something like the camera operator's head. Because he's fixed to the camera, he's going to stay pretty static within the field of view of camera, so you can get a long way doing relatively little work. Now we won't be able to fully get rid of it, that's going to be a job for the later comp workflows video, but we can minimise the amount of paintwork we have to do by reducing the number of views which are converging in this area. And the reason why you can see some ghosting around the edges here is that this guy is really close to camera, and our convergence is set to be a decent depth for the hero elements within the shot. So what we'll do is we'll reduce the number of cameras which are showing this so as to reduce the ghosting we're seeing. So this guy is present in these two cameras, and we can see that camera 9 covers it a bit better than camera 8 in that overlap, and camera 10 barely touches on it. So what we'll do is we'll pop into camera 8, we'll drop in a roto node, and we'll turn on the mask overlay, and we'll quickly sketch around this guy here. Nice and quick, and we'll say that we want to zero out I alpha here, grab these bits, and then we will just soften them out a bit. Looks good. And now we'll do the same thing for input 3 here. There's really not much to deal with here, but why not? And we will just pop in here, like so. And again, we'll just soften that out, like so. And now we can restitch our result with these masks in place. So now the fella's head will be coming from a single camera view, so we'll have less work to paint out down the line. And now, given the guy's head is predominantly based in a single camera view, you could even go away and patch it out within that view using some kind of camera tracker based patch for that region, which would reduce even further the amount of work you have to do to the stitch afterwards. The second place you can work on manual stitch fixes is down here, between the stitcher and the blender. Here, the stitcher has applied the vector-based warps to convert your source image to Lat Long, which means that you're best applying fixes that are static once you're in this Lat Long space. In this particular case, we don't really need to bother, but you might want to, for example, apply some masking around the edge of this fella's arm here, perhaps. Or maybe apply a spline warper so you could actually go in there and realign one camera view to another. The thing to take away from this is that you're able to use any of Nuke's full arsenal of tools for patch-ups and fixes within each of these single view spaces. Another couple of potential gotchas are that right now the workflow I've outlined covers monoscopic stitches. For stereo stitches, such as the one we're looking at, the cam views that we've been looking through are the individual layers used for the view defined as left here. To manually patch the right hand side right now, you'll need a second stitcher with the left and right views flipped here. Once you do that, the cam views output from that stitcher will contain the layers that go into the right hand view, ready for your manual patch-ups. The other gotcha is that you have to take into account the effect of stabilization ops. This one will be covered in more detail in one of the later videos in this series, but bear in mind, if you apply stabilization pre-stitch, your stitch edges, i.e. the edges of the individual cameras, will end up moving around in this final lat long and may make your patchwork harder. In turn, you may want to apply the stabilization as a post-process. Because generating vectors in the stitcher can be expensive, you may find that it's helpful to pre-cache post-stitcher, so after the stitcher here, but before any of your manual patchwork in that lat long space. By doing so, you can ensure that when you're working on this patchwork, it'll just be hitting a pre-cache result rather than going upstream and potentially having to calculate that data over and over again. As with most things in Nuke, there's a bunch of different ways to do this, so I'll just show you my favourite, which is using multi-view EXR files, as I like being able to wrap up all the views in a single file. Bear in mind that these files get pretty big, however, due to all the views, so you'll want to have speedy drives. So I'll add a write node, and I will write out a SXR sequence, which is multi-view EXRs. One useful aside is that when you have CARA VR installed, you get this little tab on all write nodes. Now this is because Nuke's views knob here gets a bit clunky to work with when you've got a lot of views, because you have to go in and manually toggle each one and off individually. This tab here allows you to set up preset versions of that, so I could just set the main view. That'll be writing out just my main. Alternatively, I could tell it to write out just my left and right views, like so. I could tell it to write out all of the cam views, or I could reset everything and just go back to writing out every single view. In this case, we're going to stick with that. Also, another Nuke gotcha. For multi-view EXR files, Nuke will only write out the channel sets it finds in the first view for all of the views. This won't matter in this case, but let's say we wanted to write out the stitch map channel that you get on Cam 1, Cam 2, Cam 3 from the stitcher, and contains the UV data so that you can reapply that whole warp to the original source image should you so desire. Well, to do that, you'd obviously need to pick all channels up here, but you'd also need to go in here and do a split and join beforehand and add the stitch map channel to the first view. That way Nuke will know to write out those channels in all the views. At this point, I can go away and hit render, which will render out all those different views to a single per frame file. And then I can toggle on read file here. And this will mean that when rendering downstream, it'll only go up so far as to hit this read node, or rather write node set to read here, without going up and actually calculating any more image data from up here. It will, however, go and calculate the hash for this upstream tree. And you can think of the hash as the fingerprint for that tree. So if you were to go in here and change one of the knob settings, that will change the hash. And what's really useful about writing to an EXR file is that it's got a bit of metadata in there which records the hash with which it was written. And you can see that if somebody changes a knob setting up here, this read from write node will know that the hash in the header of the EXR file won't match the hash of the tree, and so it'll error. But of course you can toggle that check off if you so desire, or even disconnect the input to the write node, whatever works for you. To wrap up this video, I want to touch on one final option, which is using the Lat Long Space options in the Camera Solver and Stitcher. Rather than outputting the source view projection on the cam views, I can instead choose to reproject it directly to Lat Long inside of my solver, here. What this means is that then the Cam 1 through Cam whatever views that we split out here, rather than being in source space, will actually be in Lat Long space. Colorimeter and Stitcher should handle this automatically as well, based on the metadata in the stream, but you can also force them to expect a particular incoming format. Looking at this example here, you might want to do this if you wanted to do some manual patch-up work in Lat Long space without the vectors applied, and then use that final pass of Stitcher just to apply a final deghost stage. Similarly, you might want to do this if you've actually got your source images reprojected into Lat Long space through some other stitching program. You can then wire those into the Stitcher here, using, of course, the appropriately named views, and then using CARA C Stitcher to apply a final deghost pass to that pre-existing set of stitch layers. You might also want to do this in a similar way to this example here, where we've been doing manual patch fix-ups. Let's say you don't actually think you need the C Stitcher final deghost stage, so you're going to output Lat Long from C Solver, do some final patch-up fixes in here with, say, spline warp or roto, and then use the C Blender pass to pull all those together into your final stitch. It's a trade-off though. If you're going to use both Camera Solver and Stitcher and convey the intermediate camera data in Lat Long, then bear in mind that you're actually now going to be filtering your images twice. Once in the Camera Solver to take it into Lat Long space, and then again in C Stitcher to take it from Lat Long space to Lat Long space with the final warps to deghost it applied. In the default chain, where you stay in source space, of course, you only apply those warps once in C Stitcher. So there we have it. We've finalised our stitch for this shot with a few more advanced techniques, and we've covered the intended manual patch-up workflows that you can use when stitching with CARA inside of Nuke.